Okay, so we learned that the derivative of natural log of x is 1 over x. That's what we did before, okay, in 5.1. So look at this log rule for integration. If you start with 1 over x and you have to anti-derive, remember this is basically saying whose derivative is 1 over x? Natural log of x. Okay, and then of course we have our little plus c there. The absolute value bars, what are those for? Why is it important that we take natural log of something that's positive? Yeah, the domain of natural log is only positive numbers. You cannot take natural log or any other log of negative numbers or even 0. So I'm going to kind of explore this whole idea of when to write the absolute value bars and then why sometimes you see them and sometimes you don't. But I'm going to kind of do this in the context of problems. So before we get to this more complicated rule, let's just look at number 1. How is number 1 different than the rule? There's a 5. So let's move the 5 out. And let's rewrite it without the 5 inside the integral. So we can do that with numbers. We cannot do that with x or trig or anything, but we can do that with 5 or 2 or whatever, or even a negative. So if we look kind of what we just went over, the antiderivative of 1 over x, or the integral of 1 over x, is natural log of x. So that's our answer. Make sure you put that x in absolute value bars. The only time you can drop the absolute value bars is when you are 100% sure that what you're writing here is always going to be positive. Okay, so an x could be positive or could be negative. What if this had been x squared? That would always be positive. So you could write the absolute value bars or you could leave them off. Okay, most of you are just going to write them every time because it doesn't hurt if you write them and you actually don't need them, okay? But that's why sometimes you're going to see them and sometimes you won't. Okay, we could easily check this by taking derivative. We get exactly what we started with, maybe a little simplification there. All right, so let's look at example 2. Okay, it's a little bit more complicated, and it has to do with this rule up here. All right, there's a couple of different ways to write this rule. I'm going to box this one because I think this is what most of you are going to really think about. Integral of 1 over u du, that's very similar to 1 over x dx. That antiderivative is natural log of u. And when we see u, we should be thinking about u substitution. So where is the u in this problem? Like the location. The denominator. So let's see if we can get 2 to integrate using u substitution. And let's let u be the denominator. So this is new. We haven't used this before. Before, we always let u be the thing in parentheses. We let u be the power on e. Now we have a new tool in our toolbox, and it is called let u be the denominator. All right. So then the next step would be du. So this we should be very comfortable with by now. What's du? 5 dx. So the dx is going to be replaced by, well, there's no 5 here, so let's divide it over. So the dx gets replaced with 1/5 du. The 1/5 gets moved out to the front, just like as if we did any other u substitution problem. So remember, we let u be the thing in the denominator. So what we are left with is 1 over u du. That's what you want. You don't want to have any x's mixed in with your u's here. If that's the case, you either did something wrong or it was supposed to be a TOCO problem. Okay, so but this is just, everything got swapped in and out. All right, so then what is the antiderivative of 1 over u? Natural log of u. So natural log, absolute value of u. And then our very last step here would be to go ahead and instead of u, write in 5x plus 3. And again, 5x plus 3 could be positive, could be negative, so we really do need the absolute value bars. If that had been 5x squared plus 3, it would have been okay to drop the absolute value bars and put parentheses in place. Mm-hmm. Okay, so so the question is, if this was multiple choice, might they use the log property that puts this 1/5 as the exponent? I've never seen them do that with 1/5, but I have seen them do that with 2, or maybe even 1/2, because then that would cause a square root situation. We're gonna go over that in a later problem where I give some multiple choice answers, but that's a great question. You're right, there always can be simplification of these logs using log properties. Okay, so let's look at number 3. Without trying to think about how to do every integration problem in the world, let's just think about what we've done so far today. What do you think U is going to equal? Why? The denominator. I just said, hey, let's just do it the same way we did last problem, right? That's basically what I said. Now, if we let U equal something and it ends up being the wrong choice, we will be able to figure that out. We'll get stuck or something won't work out, okay? That's not an answer people like to hear, but it is the truth. So let's go ahead and do the du and see if we get a match. So if we take derivative, we have 2x plus 6, and then dx. Well, I don't see a 2x plus 6, but I do see an x plus 3. So the question is, did we make a mistake, or is there some simple algebra step we could do to make it happen? Yeah, they're so smart. So we can factor out the 2 and get x plus 3. And then this 2, just like any other time, we can divide over. The reason this works out is because now I have an x plus 3 dx, and right here I have an x plus 3 dx. That should match up. If it doesn't match up, we did something wrong, or possibly it's a TOCO problem. But that's not the case. Everything's working out perfectly. The 1/2 needs to get moved to the front. Don't get ahead of yourself. Go ahead and just write it as 1 over u du. All right, because remember, we let the denominator be u. A common mistake here is sometimes students, instead of writing 1 over u, they just write u. All right, what's the antiderivative of 1 over u? This is the new thing today, natural log of absolute value of u plus c. And that becomes 1/2 natural log absolute value of x squared plus 6x plus c. And again, you could check your work by deriving. I'm not going to spend a lot of time here going over that. Just as a reminder, though, when you are deriving, you've got to do like 1/2, 1 over x squared plus 6x, and then go times the derivative of the inside. And what you have should be exactly what you started with. All right? So if we did derive, it would look like this. Okay. So I want you to try 4 on your own. We have not done a trig problem today, so you're going to have to combine what you know about trig versus U substitution versus what we learned today, and try your best. All right, so I saw a lot of u equals tan x, and then I saw a lot of people not quite sure what the derivative of tan x is. That's vital to this problem. You just got to know this. Did you figure out what I was saying?
Yeah.
It's right.
It's on that thing.
Oh, okay. It's.
Oh, you mean? Oh.
Yeah. You see it? Okay.
Okay.
Okay. So then we have 1 over u du, which is the same as natural log of absolute value of u plus c, natural log of absolute value of tan x plus c. Okay, I want to show something with this. Not everybody was able to get it, but most of you were able to do something with this. We had never done an integral natural log trig problem before. Why were you able to do it?
Because it was already so easy to alter it.
Because you combined different topics into a new problem. When you get to a problem you don't know how to do, you just can't, it's defeating to think, I don't know how to do this because I don't think we ever did one like this, or I don't remember how to do this one. You've got to be able to think it out. So keep that in mind with number 5 here. All right, so let's do this one together as a class though. Any ideas on number 5, what we should let u equal?
Yeah.
Okay, so there's kind of 2 different things in our toolbox. One of our tools is let u be the entire denominator. What's the original tool for u substitution? Parentheses. So don't write this down, but just watch what I'm going to do right here. Let's say we get caught up with this whole let u be the denominator, and I apply it to this problem. This is going to be a mistake, but we're going to figure out why. If I do du, I'm going to need to do 2, keep the inside the same, decrease the power by 1, multiply by the derivative of the inside. I have a problem here. I have a problem because although this is a 2x up here, listen, although this is a 2x up here, I don't have a plus 2. When you have extra things in your integral, that's a TOCO. When you have extra things down here, that's you can't do it. Okay? So this was not a good u to pick. That's how I know it didn't work out. I had too much, it wasn't swapping in and out. So the other tool in our toolbox is to just let u be the thing in parentheses. So we can't forget about that stuff. All right, so let's let u be x plus 1. So remember what I was saying. It's not about, you've never done one like this, but we're going to work through it and it's going to be okay. So if u is x plus 1, what's du? 1 dx. I'm just going to write the dx. Okay, so a couple of things. First of all, let's go ahead and put a u down there. I'm going to replace that. So I'm going to have, in a minute, I'm going to have a u squared in the denominator, which is already different than the other problems. Before I just had a u. Okay, the dx is totally getting swapped out with the du. Now the 2 I can handle. The 2 can be moved to the front. That's fine. My problem is I have an extra x. So what type of problem is this? TOCO. You're not going to be told from now on when you have TOCO. You're going to have to be able to figure it out. So the first thing is figuring out that this is TOCO. The second thing is, well, what do we do about it? I have an extra x. I have to replace x with something relating to u. So that means I need to figure out, well, what does x equal? Now remember, u equals x plus 1, so x equals u minus 1, and that's what's going to go on top right here. And it is quite possible that this could be multiple choice, and this is your answer, and you're done. Okay? That's not our reality right now, but that could happen. So watch what I'm going to do. Remember with TOCO, the way we finished the problem was we distributed. Okay, so watch what I'm going to do. I'm going to change this u squared into u to the negative 2.
Whoa.
All right? And then I'm going to distribute. This is similar to what we did with other TOCO problems. So what is u to the negative 2 times u to the 1? U to the negative 1. Okay, minus u to the negative 2, because it's just multiplying by 1. I'm going to go ahead and put that in parentheses so I know I'm integrating that whole thing. All right. Also with TOCO, when we did that, the only real rule we knew was the polynomial rule. Okay, so what do we do with the powers when we're integrating using the polynomial rule? What do you do with that power? You add one, right? Yeah. So you do the coefficient divided by something, and you add 1 to the power, and then that new power goes down here. And that's going to work perfectly with the second term. It's not going to work with this term right here. What's going to happen to this term when you add 1? It's going to go away, be undefined, be weird. So I want to remind you of something. I want to remind you that u to the negative 1 is the same as 1 over u, right? Okay. Excuse me. You have not been asked to integrate this before today. So today, we saw it as 1 over u, all right? But here it's written as u to the negative 1. What is that integral? Natural log of u. That was the new thing today. Okay, so let me repeat this. It was seeming to be like a normal TOCO, which is challenging, but this was just kind of working out like any other TOCO problem. Then I have u to the negative 1 in my problem. Okay, I can't do that whole add 1 to the power because that makes the power 0 and my exponent goes away. All right, and the variable u to the negative 1, same thing as 1 over u. So the antiderivative of u to the negative 1 is natural log of absolute value of u. Okay, that's what that one is. Okay, minus. Now we move on to the second one. On the second one, we can use the polynomial rule. I can do, there's like a 1 there. I can do 1 over something. I can add 1 to the power, and then I can put that new power in the denominator. Okay, so I want to, we still have one more step to go, although that's the easiest step. I want to make sure everybody understands why I did these two differently. If you add 1 to the power and you get 0, that's a red flag that you missed a natural log connection. Okay, integral of 1 over u, integral of u to the negative 1, that's new today. That's natural log of absolute value of u. So then my final answer, we just put an x plus 1. I'm going to make that into a plus here since it's minus negative. You, of course, would not have to do that. Wait, say that again. There's no natural log in the second term. They're not connected. It's like the 2 is being applied to everything, but that natural log is only connected to this first.
But then since the second term, the 1 to simplify, like in front of it, the term just like plus u to negative 1. Oh, wait, then you already took it.
Okay, are we good? Okay, sometimes you just got to talk it out. Okay, this is pretty hairy here. All right, but I don't want you to worry and think right now, well, I never would have gotten that far in this. That's not the point of why we practice these in class. It's so that you can build up those math muscles in your brain to get better and better about making connections. Okay, let's look at number 6. We have not yet done one with bounds. You're going to do this one on your own, but let's together, just to make sure everybody's on the right track, what should u equal? X squared plus 1. This is more like the others. There's really no other option for u. It has to be the denominator. There's no parentheses or anything. So I want you to try this on your own. I'm going to give you a hint about you have to change the bounds here if you do u substitution. Okay, 1/2 goes in front. We end up with 1 over u du. Everything matches up quite nicely. What were your new bounds? 10 and 1. That's because 3 squared plus 1 is 10 and 0 squared plus 1 is 1. All right, now we still have to integrate. This is actually where I think a lot of people make their mistake. They understand how to integrate, they just forget to do it. So that excuse me, that becomes natural log of u. And then we don't need the plus c because I'm going to actually plug in numbers here. If you wrote plus c, that's okay, but you don't need it. All right, now, what do you think about me writing 10? Do I have to put in absolute value bars?
No, because it's a positive.
10's positive, so it's fine. If you keep the absolute value bars, that's fine too. I'm not going to write them though. I want to talk for just a second about if this was multiple choice. It wouldn't be, you'd need to simplify. So the obvious thing to simplify would be that natural log of 1 is 0. So it could be that your multiple choice could be like this. I'm just simplifying for multiple choice purposes. It could even be that they use a log property. This is what you were talking about, Peyton, earlier. If I wanted to get rid of the 1/2 here, it's possible they could move it to right here and then even call that square root of 10. All of these are equivalent. I don't care that you are clever enough to come up with that. That's not a big deal. You're not going to do that because I don't want you to. I don't want you simplifying unless it's multiple choice or unless you're specifically told to simplify. What you've got to be able to do, though, is in a list of multiple choice options, you've got to be able to look at something like this and go, yep, that's the exact same thing as what I have. That's what you need to be able to do. That's why we focus on simplifying.
We could have done quotient thing and then another thing.
Okay, let's go to the next page. We have one more example to do today. We're not going to quite finish with all our examples, but I think one more today would be good. Good place. All right. For our trig, was there anything that when I took derivative, I got tan x only?
Sin x over cosine x.
Okay, so hang on to that thought, but that's not my question. That's how we're going to overcome. Was there anything that when we took derivative, we got tan x? No. So I don't know what that antiderivative is, so I'm totally stuck unless I rewrite this. And with trig, that means using identities. Okay, so there's one identity with tangent that's one we use a lot more than the others. You don't have to have every identity memorized. This is one for sure you should know. That tan x is the same as sin x over cosine x. Okay, now we have a fraction. And now we can let u equal, again, the denominator. So that would mean that u is equal to cosine x. You got to let u be the denominator because your du, which is negative sine x dx, the negative we can get rid of easily. We can just move it to the front. Okay, but when you look at what's left over here, it only really works if what you have is in the numerator. So a lot of people on this would say, well, wouldn't it be easier to let u equal sine x and then we wouldn't have to deal with the negative? The problem is your du is in the wrong place then. Okay? So if we do it like this, it turns into a simple problem. The first step on this, rewriting this and using a trig identity, is the hardest part. Okay, so what would be my next step? Natural log of u, and again, there's no bounds or anything, so I need to go ahead and put plus c. And then my very last step is to replace u with what I said u was supposed to equal, which is cosine x. Right.